Welcome to AudioCert, where the official study guides are brought to life.
And today we're kicking off a really important series. We're diving into what's arguably one of the most critical certifications out there right now for security professionals.
Yeah.
The Certified Cloud Security Professional, the CCSP.
Absolutely. And this deep dive is specifically for you listening in. Whether you're deep in exam prep right now, or maybe you just need a solid grasp of the cloud architecture that, let's face it, runs so much of modern IT. We're starting right at the beginning. Domain 1, Cloud Concepts, Architecture, and Design. And first up is Chapter 1, Architectural Concepts.
Right. And look, if you're already in the security game, maybe you've got your CISSP or just years of solid InfoSec experience. You get the fundamentals, risk management, governance, the basics. Yeah. The CCSP kind of assumes you have that baseline. But, and this is crucial, this first chapter, it's absolutely foundational. Non-negotiable, really. It sets the stage. It defines the specific language, the particular ways of thinking, the models that make cloud security different from, traditional on-prem security. It's all about the CCSP common body of knowledge, the CBK terminology here.
So it's more than just definitions. It's about establishing that common ground, that specific viewpoint needed for the rest of the certification.
Exactly. Our mission today isn't just to read terms off a page. It's to really get under the hood, understand the why these 5 characteristics matter, why the service models are structured the way they are, the different deployment frameworks. If you can grasp the architecture, the vocabulary, and the underlying reasons, the economics, the operational shifts, then understanding the security controls later on becomes so much easier.
Makes sense. Build the foundation first.
Yes.
So where do we start? I guess with the official definition.
That's the place. We have to start with the benchmark, the definition from NIST, the National Institute of Standards and Technology. Specifically, NIST Special Publication 800-145. This definition is, well, it's pretty much the law of the land for defining cloud computing.
Okay, lay it on us.
All right. NIST 800-145 defines cloud computing as a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources. Things like networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction.
Okay, that's quite a mouthful. Ubiquitous, convenient, on-demand, shared pool, rapidly provisioned, minimal management effort. There's a lot packed in there.
It really is. And those phrases aren't just jargon. They actually contain the 5 essential characteristics that define what makes something cloud. These aren't just nice-to-haves. They are the defining traits.
All right, let's break them down then. What's the first one? Access right.
First up is broad network access. This basically means the services have to be accessible over the network using standard common mechanisms. Think web browsers, standard APIs, and critically, it shouldn't matter what device you're using, a laptop, a phone, a tablet, or where you are. London, Tokyo, your home office.
So no proprietary hardware or weird protocols needed. It just works over the internet using the tools we already have. How do providers actually achieve that kind of ubiquitous access?
Yeah, good question. They use things like heavy-duty load balancers to distribute traffic, content delivery networks, CDNs, to cache data closer to users, and often geographically dispersed data centers, multi-site hosting, so the connection path is shorter and more reliable, no matter where the user is connecting from.
Broad access. Makes sense. What's next on the list from that NIST definition?
On-demand self-service. This is a huge departure from how IT used to work. We're putting in a request for a new server and waiting weeks.
Oh, yeah. Purchase orders, approvals, waiting for delivery, racking it. Nightmare.
Exactly. On-demand self-service means you, the customer, can provision computing capabilities, maybe more storage, stood up virtual machines, adjusting network settings automatically whenever you need them, usually through a web portal or an API call. And the key part is, with minimal .service provider interaction, you don't need to call someone or file a ticket to get more resources. You just do it yourself instantly.
That's powerful. That real-time control. Okay, so broad access, self-service. What else makes it cloud?
Now we get to the real engine behind the economics of cloud, resource pooling. This is often talked about as multi-tenancy.
Ah, multi-tenancy. I hear that term a lot. What does it mean in practice, especially for security folks?
It means the provider takes these massive pools of physical resources, servers, storage arrays, network gear, you name it, and dynamically assigns them to multiple customers, multiple tenants as needed. You, Company A, might be using CPU cycles on the same physical server blade as Company B, your direct competitor, without either of you necessarily knowing it.
Right. So the provider buys big, shares the hardware, and passes the savings on.
That's the core financial model, yes. It avoids waste. Instead of every company buying servers that sit idle 80% of the time, the provider aggregates that demand and keeps their hardware utilization much higher. That's how they make it affordable.
But okay, from a security standpoint, sharing physical hardware sounds inherently risky. My data is on the same metal as someone else's.
That's the fundamental security challenge of public cloud. The risk of lateral movement between tenants, or something called hypervisor escape, where maybe a vulnerability allows one virtual machine to somehow affect or access another VM on the same host. It's the provider's absolute core responsibility to build and maintain really robust logical separation between tenants. That's paramount. We'll talk way more about hypervisor security later.
Okay, so pooling resources is key financially, but brings security challenges.
Yeah.
Got it. What's the fourth characteristic?
Speed. Yeah, speed and flexibility. Rapid elasticity. This is about scaling. The ability for your cloud resources, the amount of storage you use, the number of users you support, the compute power you consume to scale up or down rapidly, sometimes automatically based on demand.
So if my website suddenly gets featured on the news and traffic spikes?
The cloud platform can automatically add more web server instances, more database capacity, whatever is needed, almost instantly to handle the load. And just as importantly, when the spike is over, it scales back down. Compare that to the old way, frantically trying to buy and install servers during the crisis. Elasticity avoids being caught under-resourced or paying for excess capacity you don't need most of the time.
That ability to scale instantly seems amazing, but it only really works financially if you're not paying for that peak capacity all the time, right?
Exactly. And that leads directly to the fifth and final characteristic: measured or metered service. Think of it like your electricity bill. You only pay for what you actually use.
Utility computing.
Precisely. Cloud systems automatically control and optimize resource use, and they have mechanisms to measure usage at a granular level: storage used, compute hours consumed, network bandwidth transferred. This means you, the customer, are billed only for the resources you consume during a specific period. If you scale up massively for 2 days, you pay the higher rate for those 2 days, then it drops back down. You don't pay for idle capacity you might need someday.
That really flips the traditional IT finance model on its head.
Completely. It shifts the risk of over-provisioning from the customer to the provider.
Let's solidify this with that classic example you mentioned, the online retailer during the holiday shopping rush, like Black Friday. How do elasticity and metered service work together there?
Okay, imagine a big online store. Most of the year, maybe January through October, their website traffic and sales are pretty predictable, fairly stable. They need a certain baseline level of compute and database power.
Standard operations.
Right. But come late November, Black Friday hits, Cyber Monday follows. For maybe 48, 72 hours, their traffic explodes. 10 times, 20 times the normal load. Orders flooding in.
Total chaos, potentially?
Could be. But if they're on a public cloud platform, they leverage rapid elasticity. Their system maybe automatically scales up massively, spins up dozens, hundreds of extra web server instances, scales out the database replicas, increases network capacity. It handles the surge.
Okay, they survive the rush, but isn't that incredibly expensive?
That's where measured service comes in. They pay that significantly higher cost, reflecting the tenfold resource usage, only for those 48 or 72 hours. As soon as traffic drops back to normal levels after Cyber Monday, the system automatically scales back down. The extra instances are terminated, database capacity shrinks, and their bill immediately reflects the lower baseline usage rate again.
Wow. Compared to the old way.
The old way. They'd have to buy and maintain enough hardware to handle that absolute peak load, that Black Friday surge, all year round. Imagine 10 times the servers just sitting there, powered on, depreciating, doing almost nothing for 363 days of the year. The cost saving with the cloud model is just immense for businesses with variable demand.
That makes the economic driver crystal clear. #2, business requirements and cost-benefit analysis. And that economic driver, that cost saving, it leads us right into a really fundamental principle emphasized in the CCSP materials, the absolute priority of business requirements. I remember reading that security is always, always a support function.
That is probably the single most important governance concept to internalize for the CCSP, and frankly for any security role. Security exists to support the business mission, not the other way around. Think about it. Almost every security control we implement adds some friction. It slows things down, it restricts access, it costs money and resources.
Passwords, multi-factor authentication, firewalls, they all add steps or block things.
Exactly. They hinder efficiency by design. Therefore, every security decision, every control we choose, every dollar we spend on security must be driven by and justified by a specific business requirement. We don't implement security for security's sake. We implement it to enable the business to achieve its objectives safely, within an acceptable level of risk.
Okay, so business needs come first. How do we typically categorize these needs? I think the terms used are functional and non-functional requirements.
That's right. Functional requirements define what a system or process must do to perform the business task. So maybe for a sales system, a functional requirement is a salesperson must be able to remotely access customer relationship data. It's about the core capability needed.
Okay, what it does.
Then you have non-functional requirements. These define the qualities or constraints of the system, how well it should perform, its usability, its reliability, and very often its security. So, building on the sales example, a non-functional requirement would be the salesperson's remote connection must be secured using company-approved VPN and MFA, or customer data access remotely must be protected according to GDPR.
Ah, so the functional is the non-functional is the how securely or how reliably,
Yeah.
and security usually falls under non-functional.
Precisely. The security requirement supports the functional need. You can't just say we need security. You need to tie it back to protecting a specific function or data asset that the business relies on.
So before an organization even thinks about moving to the cloud, they need to understand these requirements for their existing systems, right? What functions are critical? What non-functional requirements, like security or compliance, are currently being met?
Absolutely critical. That initial due diligence, understanding the current state, what assets do we have, what are the critical business processes, what are our current security controls and capabilities, is vital. You have to know what you have before you can figure out how to move it or replace it safely.
And that leads into the business impact analysis, or BIA.
Directly. The BIA takes that inventory of assets and processes and prioritizes them based on their importance to the business. It asks, what's the impact if this system goes down? What's the financial cost, the reputational damage, the legal penalty if this data is lost or stolen? It quantifies the potential harm.
So it identifies the crown jewels, the critical paths, maybe single points of failure.
Exactly. And by putting a potential dollar value on downtime or data loss for each critical asset, the BIA gives senior management the data they need to make informed decisions about risk, and crucially, to justify spending money on the necessary security controls in the cloud migration plan. It translates technical risk into business language.
Okay, so once we understand the requirements and the potential impact of things going wrong via the BIA, then we can start building the cost-benefit case for moving to the cloud. A big part of this seems to be the shift in spending, from CapEx to OpEx.
Yes, this is a huge strategic driver for cloud adoption. Let's break it down. Traditional IT spending is primarily capital expenditure, CapEx. You buy physical assets, servers, routers, firewalls, storage arrays. You pay a large sum upfront.
And that equipment depreciates over time.
Right. From an accounting perspective, the cost is spread out over the asset's useful life, usually several years, via depreciation. You get tax benefits slowly, and you carry the risk. You might buy too much hardware that sits idle or not enough and get overloaded.
Okay, that's CapEx. How does cloud change that?
Cloud shifts the majority of that spending to operational expenditure, OpEx. You're not buying hardware, you're essentially renting computing services. It's like paying a utility bill, an ongoing operational cost.
And the big financial advantage of OpEx is...
From a tax perspective, OpEx is generally treated as a current business expense, meaning it can be deducted from revenue in the year it's incurred. This can improve cash flow compared to waiting years for depreciation benefits.
So, faster tax benefits, but what about from a budgeting and agility standpoint?
That's often even more significant. CapEx decisions usually involve long, complex budget approval cycles, multi-year planning. OpEx, because it's tied to actual usage, thanks to measured service, allows for much greater flexibility. Need to scale up for a short-term project. It's an operational decision, often much faster to approve and implement than a capital purchase. It aligns spending more closely with immediate business needs.
But doesn't that make budgeting harder? OpEx can fluctuate month to month based on usage, whereas CapEx, once you've bought the gear, is more predictable, even if it depreciates.
That's the trade-off, absolutely.
Yeah.
You gain flexibility, but potentially lose some budget predictability. Finance teams often grapple with this. It makes forecasting more complex. That's why understanding usage patterns and having really tight service level agreements, or SLAs, which we'll definitely get into later, become incredibly important to manage potential OpEx volatility. You need mechanisms to control those costs.
Okay, so it's not a simple OpEx is always better. It's a strategic financial shift with pros and cons.
Precisely. It depends on the organization's financial strategy, risk tolerance, and need for agility.
Now, you mentioned mixing CapEx and OpEx. Let's talk about cloud bursting. That sounds like a hybrid approach.
It is. Cloud bursting is a specific strategy where an organization runs its normal day-to-day workload in its own private data center. That's the CapEx part, the owned infrastructure.
Yeah.
But they set up a connection to a public cloud provider. Then, during periods of unusually high demand, maybe a sudden crisis, a marketing campaign goes viral, or just predictable seasonal peaks like our retailer example,
Sure.
when their private data center capacity is about to be overwhelmed, the workload automatically bursts out into the public cloud. They temporarily rent additional compute capacity, that's the OpEx part, only for as long as needed.
So they get the control and predictability of private infrastructure for the baseline, but the scalability of public cloud for the peaks without having to over-provision their own hardware permanently.
Exactly. It's a way to handle unpredictable spikes cost-effectively while keeping sensitive baseline operations potentially more isolated. It requires careful planning and integration, though.
Makes sense. Beyond the hardware cost shift, CapEx to OpEx, and bursting, what about people and operational costs? Does cloud reduce those?
Often, yes.
Yeah.
Significantly. Think about managing a traditional data center. You need staff for racking servers, managing power and cooling, handling network cabling, patching operating systems, managing storage arrays, database administration. It's a lot of specialized skills.
Yeah.
When you move services to the cloud, especially to platform as a service, PaaS or software as a service, SaaS, the provider takes over many of those underlying tasks. If you move your email to Office 365, SaaS, you likely don't need dedicated internal Exchange server admins anymore. You're outsourcing that non-core competency.
So potential reduction in specialized IT headcount or reallocation of those staff to higher value tasks.
Correct. And also, many routine operational costs, things like applying OS patches, performing hardware maintenance, basic security monitoring of the infrastructure, get bundled into the cloud provider service fee. This can make operational costs more predictable and shield the customer from unexpected expenses like emergency patching pushes or hardware failures.
The materials also mention potential savings through regulatory cost transfer. How does that work? Compliance is usually a huge cost center.
It is. And providers know this. So many major CSPs invest heavily in getting their platforms certified against various compliance regimes. Think PCI DSS for payment cards, IPA for healthcare, ISO 27 to Series 1, SOC 2, FedRAMP for government.
Okay, they get their infrastructure audited.
Right. And then they might offer specific services or configurations that come pre-validated or attested to meet certain controls within those standards. For example, you might be able to deploy a virtual machine environment that the provider attests already meets specific PCI DSS requirements for network segmentation or logging.
So by using that pre-packaged compliance service, I, the customer, inherit some of those controls and don't have to build and validate them entirely myself.
Exactly. It can significantly reduce the customer's effort and expense in achieving and demonstrating compliance for the parts of the stack the provider manages. It doesn't remove the customer's overall compliance burden, especially for their own data and applications, but it can provide a huge head start and cost saving on the infrastructure layer.
Okay, that's a tangible benefit. Now, before we get too carried away with the benefits, you stressed something earlier. We need to pause and hammer home a critical legal point, the absolute red line.
Yes. Let's slow down right here. This is arguably the single most important takeaway regarding risk in the cloud. No cloud customer can ever transfer the legal liability or ultimate responsibility for the protection of personally identifiable information, PII, or protected health information, PHI, or sensitive financial data, whatever the regulated data type is.
So even if I sign a contract where the provider says they're responsible for security, if there's a breach of my customer's PII that resides on their servers, I'm still the one on the hook legally.
You, the organization that collected that PII from the data subjects, are the data owner or data controller in legal terms. You remain legally and financially responsible to the regulators, like under GDPR or CCPA, and to the individuals whose data was compromised, period.
Even if the breach was 100% the provider's fault, like they failed to patch a known vulnerability on the server hosting my data.
Even then. Now, the provider might be contractually liable to you under the terms of your contract. And SLA. Maybe you get service credits. Maybe you can sue them for damages they caused you. But the fines from regulators, the lawsuits from affected individuals, the mandatory breach notifications, the reputational damage that primarily lands on the data owner, the customer organization, you cannot outsource that fundamental accountability.
Wow. Okay, that has massive implications for due diligence, for contract negotiation, and for the security controls we need to implement before data even gets to the cloud. like encryption where we hold the keys.
Absolutely. It drives the need for strong, data-centric security controls, robust auditing, and very careful provider selection and contract scrutiny. It's a non-negotiable reality of cloud security.
Point taken, loud and clear. Finally, in this section on business drivers and costs, let's quickly define return on investment ROI as it relates to these cost-benefit calculations.
Sure, ROI is a standard financial metric.
Yep.
Simply put, it measures the profitability of an investment. The basic formula is net profit cost of investment, 100, expressed as a percentage. In the cloud context, the profit might be the cost savings from shifting to OpEx, reducing personnel, avoiding compliance penalties, etc. The cost is the migration expense, the ongoing subscription fees, any new security tools needed. The BIA helps quantify the potential profit from avoided losses. Security teams use ROI calculations to justify cloud migration and security spending to the business leadership in financial terms they understand. #3 Cloud Computing Service Models.
CISSP. Okay, so we've covered the 5 characteristics that define cloud and the business drivers behind using it. Now let's shift to the types of services offered. This is the as-a-service spectrum, right? Usually called SaaS.
Exactly. While you sometimes hear lots of other AES terms like network as a service, NAS, or containers as a service, the CCSP focuses squarely on the 3 core foundational service models. These models are differentiated by how much of the technology stack the provider manages versus how much the customer manages. And crucially for us, where the security responsibility shifts.
So it's all about the division of labor and responsibility. What's the most basic layer?
That would be infrastructure as a service. Think of it as the fundamental building blocks.
Like digital land, almost.
That's a great analogy. The provider gives you the raw infrastructure. The physical servers, though you interact with virtual ones, the storage, like virtual disks, the networking components, virtual networks, firewalls, and the underlying virtualization layer, the hypervisor that makes it all work. They manage the data center facility, the power, cooling, physical security.
Okay, so they handle the deep hardware in the building it sits in. What's left for me, the customer, to manage and secure?
Pretty much everything logical that runs on top of that infrastructure. You install, configure, patch, and secure the operating systems, OS, any middleware, like database engines or messaging queues, the runtime environments, your applications, and of course, all your data.
Wow, so with iGaze, I'm still responsible for patching Windows or Linux vulnerabilities, securing the OS configuration, managing application security, everything above the hypervisor.
Correct. The security responsibility for the OS and everything above it rests squarely with the customer in the IaaS model. The provider secures the underlying infrastructure. You secure what you put on it.
That sounds like a lot of work still. Similar to managing servers in my own data center, just without owning the physical boxes. What's the main use case for IaaS then?
It's often used by organizations that need maximum control over their environment, perhaps for specific compliance reasons, or because they run highly customized applications or operating systems that aren't available in higher-level models. It's also very common for business continuity and disaster recovery, BCDR, replicating your on-prem infrastructure in the cloud for failover. Or for things like long-term data archiving where you just need cheap storage and basic compute.
And cost-wise?
IaaS is typically the cheapest cloud option in terms of the raw service fee, but because the customer retains so much management and security responsibility, the total cost of ownership, including staffing, security tools, etc., might not be as low as it first appears compared to other models.
Okay, that's IaaS, the basic building blocks. What's the next step up the stack?
Platform as a service. PaaS. Here, the provider manages more. PaaS includes everything in IaaS, plus they manage the operating systems, middleware, and runtime environments.
Ah, so the provider handles the OS patching, updates, administration. That sounds like a big burden lifted.
It absolutely is. Think about keeping hundreds or thousands of servers patched and configured correctly. It's a massive operational task. In PaaS, the provider takes care of securing and managing the OS layer, the database engines, like managed SQL or NoSQL services, the development frameworks.
So my responsibility shifts up the stack again. What am I left managing in PaaS?
You, the customer, are now primarily responsible for deploying, managing, and securing your applications and your data that run on the platform the provider gives you. You still need application-level security controls, secure coding practices, access management for your apps, and data security. But you don't worry about underlying OS vulnerabilities.
What's the sweet spot for PaaS? Where does it shine?
The classic use case is software development and testing, what we often call DevOps. Developers get pre-configured environments with specific OCs, databases, and tools ready to go. They can quickly spin up isolated environments to build, test, and deploy applications without managing the underlying infrastructure or OS complexity. It dramatically speeds up the development lifecycle. PaaS also includes things like cloud-based database services or big data analytics platforms.
Okay, so PaaS is great for developers or anyone who wants to focus on applications, not infrastructure or OS management. Now the top layer, the most extracted model.
That's software as a service. So this is the model most end users interact with daily, often without even thinking of it as cloud.
Like Gmail, Salesforce, Office 365, QuickBooks Online.
Exactly. With SaaS, the provider manages everything. The underlying infrastructure, IaaS, the platform and OS, and the application software itself. They handle all the hardware, software, patching, updates, maintenance, everything.
So what's left for the customer to do other than pay the bill?
The customer's responsibility in SaaS is typically limited to managing user access and permissions within the application, configuring application-level settings, like sharing rules or data retention policies if offered, and crucially, managing and securing the data they upload or create within that application. You're essentially just a user of the software.
So minimal technical management, maximum ease of use. Ideal for standard business functions like email, CRM, HR systems.
Precisely. SaaS is perfect for deploying full production applications to end users with minimal internal IT involvement needed for the application itself. The big security challenges in SaaS revolve around identity and access management, who can access the app. Data security is our sensitive data protected within the app. Data loss prevention, DLP, preventing users from exporting sensitive data inappropriately, and ensuring the provider's data handling practices meet your compliance needs. You have the least visibility and control in SaaS, so you rely heavily on the provider's security posture and contractual agreements.
Okay, that clarifies the three main service models. IaaS, manage OS and up. PaaS, manage apps and data. SaaS, manage users, config, data. The responsibility line clearly shifts with each model. #4, cloud deployment models.
Right, so we've covered what the types of services. Now let's look at the who and where. Who owns and operates the cloud resources, and where do they reside? These are the cloud deployment models.
And there are four main ones to know for the CCSP.
That's right. The first, and probably most common one people think of, is the public cloud.
Like AWS, Microsoft Azure, Google Cloud Platform, GCP.
Exactly. In a public cloud, the infrastructure resources, servers, storage networks, are owned and operated by a third-party vendor, the cloud service provider, CSP. And these services are offered to the general public. Any organization or individual can sign up and lease resources.
And the defining characteristic we talked about earlier applies here, right? Multi-tenancy.
Absolutely. Public clouds are inherently multi-tenant environments. Your virtual machines, your storage buckets, they're running on shared physical infrastructure alongside potentially thousands of other customers. That's the economic model. Maximum sharing, maximum economies of scale.
Okay, public cloud. Owned by vendor, shared by many. What's the opposite of that?
The private cloud. As the name implies, the cloud infrastructure is provisioned for exclusive use by a single organization. It's not a multi-tenant environment. The resources are dedicated.
So all the benefits of cloud technology, virtualization, self-service, elasticity, but on infrastructure that's just for me.
That's the idea. Now, there are a few different flavors of private cloud the CCSP expects you to know.
Okay.
Variation 1 is the traditional on-premises private cloud. The organization owns and manages the hardware and software in their own data center, but they use cloud technologies like virtualization management platforms to deliver services internally with cloud-like agility.
So basically modernizing their own data center.
Essentially, yes. Variation 2 involves co-location or colo. Here, the organization owns the server hardware, but they physically place it in a third-party provider's secure data center facility. They rent rack space, power, cooling, and network connectivity from the provider, but they retain full control over their own servers and the software on them.
Why would someone do that instead of keeping it in-house?
Often for better physical security, more reliable power and cooling, or access to high-speed internet connections that might be too expensive to bring into their own building. They outsource the facility management, but keep control of the tech.
Okay. And the third variation of private.
This is where a public cloud provider carves out a physically or logically dedicated section of their infrastructure exclusively for one customer. So you get dedicated servers, storage, maybe even network segments within the public cloud provider's massive data center, guaranteed not to be shared. This gives you the isolation benefits of private cloud combined with the scalability and geographic reach of the public provider's infrastructure.
Sounds expensive.
It typically comes at a significant price premium compared to standard public cloud services, yes. It's for organizations with very high security or compliance requirements that need that dedicated guarantee.
Okay, so public, shared, vendor-owned, private, dedicated, single customer with different ownership location models. What's the third deployment model?
The community cloud. This one's a bit more specific. The infrastructure is provisioned for exclusive use by a specific community of organizations that have shared concerns or requirements.
An affinity group. What kind of shared concerns?
It could be a shared mission, specific security requirements, policy mandates, or compliance considerations. The infrastructure might be jointly owned and operated by the member organizations, or it could be hosted by a third-party provider, or even one of the member organizations, specifically for that community. Access is restricted to members only.
Can you give an example?
Sure. Think about the U.S. federal government. There are cloud services specifically built and certified to meet the government's stringent FedRAMP security requirements. Multiple government agencies might use this cloud sharing the infrastructure and costs, but it's not open to the general public or commercial companies. The shared need for FedRAMP compliance defines the community. Another example might be a group of universities collaborating on research using a shared high-performance computing cloud. Or maybe the financial services industry setting up a specific cloud to handle certain types of regulated transactions securely among member banks.
Got it. Shared purpose, restricted access, like a private club cloud. Okay, one model left.
The hybrid cloud. And honestly, this is probably the most common deployment reality for many large organizations today. A hybrid cloud is simply a composition of two or more distinct cloud infrastructures, public, private, or community, that remain unique entities, but are bound together by technology that enables data and application portability between them.
So mixing and matching.
Exactly. Maybe an organization keeps its highly sensitive customer database and core financial systems running on a private cloud for maximum control, but uses a public cloud POTHIS environment for developing and testing new, less sensitive applications for cost efficiency and speed. Or they use the public cloud for scalable front-end web servers while connecting back-to-back-end systems in their private cloud. Cloud bursting, which we discussed earlier, is a classic hybrid cloud use case. It's about leveraging the best of different models for different needs. #5, roles, definitions, and foundational technologies.
Okay, we've got the characteristics, the business drivers, the service models, AS, POS, SaaS, and the deployment models, public, private, community, hybrid. Now, to really understand how security works across these, we need to clearly define the key players, the roles involved.
Absolutely. First, the obvious ones. You have the cloud service provider, CSP, that's the vendor, the company owning and operating the cloud infrastructure. AWS, Azure, Google Cloud, Rackspace, etc. They're responsible for securing the underlying infrastructure they manage, depending on the service model.
And on the other side?
The cloud customer. That's the organization or individual purchasing or leasing the services from the CSP. They're responsible for securing what they put in the cloud, again, depending on the service model and deployment model.
Okay. Provider and customer. Are there intermediaries?
Yes. One common role is the cloud broker. This is a company that acts as an intermediary between the customer and one or more CSPs. They typically don't own the infrastructure themselves.
What do they do then? Resell?
Often, yes. They might purchase services in bulk from a CSP and resell them, sometimes adding value like technical support, integration services, specialized consulting, or maybe simplifying the billing across multiple cloud services. They can act as a single point of contact and management for customers who might find dealing directly with large CSPs complex.
Interesting. Now, there's another intermediary role that sounds critically important for security, especially given everything we've discussed about lost visibility and control. The Cloud Access Security Broker, or CASB, this seems like a big deal for the CCSP.
It is huge. CASBs have emerged as essential security components specifically because organizations are moving assets outside their traditional network perimeter into cloud services they don't directly control. The CASB acts as a security policy enforcement point, sitting logically between the cloud customer's users and the cloud provider's services.
So it watches the traffic going to and from the cloud. What functions does it provide?
CASBs typically operate on 4 key pillars, which you really need to know. Pillar 1 is visibility. They discover and monitor all cloud services being used, including shadow IT services users adopt without approval, and analyze usage patterns to identify risky behavior or policy violations.
Okay, seeing what's happening. Pillar 2.
Compliance. CASPs help organizations enforce their regulatory and corporate compliance policies on cloud usage. This often involves integrating data loss prevention, DLP capabilities, to identify and block sensitive data, like PII or intellectual property, from being inappropriately uploaded to or shared from cloud services.
Makes sense. Preventing data leakage. Pillar 3.
Data security. CASBs can apply additional security controls to data stored in the cloud or in transit. This might include enforcing encryption, applying tokenization to sensitive data fields, or implementing context-aware access controls, like blocking downloads to unmanaged devices.
Adding layers of protection. And the final pillar.
Threat protection. CASBs use threat intelligence feeds, behavioral analysis, eBay user and entity behavior analytics, and malware detection engines to identify and block threats targeting cloud services. This could involve preventing users from downloading infected files, blocking access from compromised accounts, or identifying malicious insider activity. They often integrate tightly with identity and access management IAM systems to provide capabilities like single sign-on, SSO, or adaptive authentication based on risk.
Wow. Okay, so visibility, compliance, data security, and threat protection. The CASB really tries to reimpose that security control and visibility that organizations lose when they move to the cloud. It sounds essential.
For organizations with significant cloud adoption, especially across multiple SaaS applications, a CASB is increasingly considered a mandatory security control.
Good to know. One more role mentioned, regulators.
Right. These aren't direct players in the transaction, but they're critical influencers. These are the governmental bodies, like the FTC, SEC in the US, or data protection authorities in Europe, or industry bodies, like the PCI Security Standards Council, that create and enforce the laws, regulations, and standards, HIPAA, SOX, GDPR, PCI DSS, etc., that dictate many of the security requirements, those non-functional requirements we discussed, for handling sensitive data, whether it's in the cloud or not. Auditors, both internal and external, also fall into this category, verifying compliance.
Okay, got the key players. Now let's nail down a few more critical definitions related to using cloud services, especially around movement and resilience. We touched on resource pooling earlier. What about cloud portability?
Cloud portability is the ideal state, what customers want. It's the ability to move your workloads, applications, and associated data relatively easily from one cloud provider to another, or maybe even move them back to your own private cloud or on-premises environment without substantial rework or cost.
So freedom of movement, what prevents that?
That's vendor lock-in. This occurs when a customer becomes dependent on a specific CSP's proprietary services, APIs, data formats, or even contractual terms, making it technically difficult, prohibitively expensive, or legally complex to migrate away to an alternative provider. Using unique features of one cloud that don't exist elsewhere is a common cause of lock-in.
So you're stuck. That sounds bad. Is there something worse?
Oh yes, vendor lockout. This is the nightmare scenario. Lockout happens when a customer cannot access or recover their own data from the cloud provider at all.
How could that happen?
The provider might go bankrupt and suddenly cease operations. They might be acquired, and the new owner decides to shut down the service you were using. There might be a major technical failure or disaster at the provider without adequate backups accessible to you. Or maybe even a legal dispute leads the provider to deny access. Lockout represents a catastrophic loss of control and data.
Okay, avoiding lock-in is important for flexibility, but avoiding lockout is absolutely critical for business survival. This highlights the need for robust exit strategies and data escrow provisions in cloud contracts.
Absolutely essential. You need a contractually guaranteed way to get your data back in a usable format if the relationship ends for any reason.
Now, amidst all these new cloud concepts, we shouldn't forget the basics. The CIA triad confidentiality, integrity, availability still applies, right?
Fundamentally, yes. The goals remain the same, but how we achieve them and where the responsibilities lie changes significantly in the cloud.
How so? Give us the cloud perspective on CIA.
Okay, confidentiality. Protecting data from unauthorized disclosure. In the cloud, since your data resides on someone else's hardware, this relies much more heavily on strong encryption controlled by the customer. Encrypting data before upload, managing your own keys, robust access controls, and potentially technologies like data masking or tokenization. You can't rely on just physical security of the server room anymore.
Right. Encryption becomes paramount. What about integrity?
Integrity. Ensuring data is accurate, complete, and hasn't been improperly modified. In the cloud, this still involves technical controls like hashing and digital signatures, but also relies heavily on the provider's operational processes, their change management, their internal access controls, their logging and monitoring to prevent unauthorized changes to the underlying platform or your data. Strong auditing and version control become crucial.
And availability.
Availability. Ensuring systems and data are accessible when needed. On-premises, you worry about your own server uptime, power, network. In the cloud, availability is largely dependent on the provider's infrastructure resilience. Their redundant networks, power systems, data center distribution, their ability to handle DDoS attacks, their disaster recovery capabilities. Your primary control here is the Service Level Agreement, SLA, which contractually guarantees a certain level of availability from the provider. If the provider has an outage, you have an availability failure.
So the how changes dramatically. Let's talk about the core technology that makes those provider economics work. Virtualization.
Virtualization is the magic behind the curtain. It's the technology that allows a CSP to take one incredibly powerful physical server, a host, and carve it up into many smaller, independent, software-based simulated computers called virtual machines, VMs, or instances. Each VM runs its own operating system and applications, thinking it has its own dedicated hardware, but in reality, they're all sharing the underlying physical host's CPU, memory, and network resources.
And that's how they achieve that resource pooling and rapid elasticity, by managing VMs as software.
Exactly. When a user logs off or a VM is no longer needed, it can be paused, shut down, or even deleted almost instantly. Its state can be saved as a file. New VMs can be created from templates in minutes. This software-defined nature provides the flexibility and economy of scale that underpins the entire cloud model.
But virtualization isn't without risks, right? You mentioned hypervisor escape earlier. What else should security pros worry about with virtualization?
Besides the critical risk of hypervisor escape, one VM breaking out to attack the host or other VMs, another major operational risk is VM sprawl. Because it's so easy and fast to create new VMs, that on-demand self-service, developers or sysadmins might spin up VMs for temporary tasks and then forget to decommission them.
Leaving orphaned, potentially unpatched and unmonitored systems running.
Precisely. These forgotten VMs increase the attack surface, consume resources unnecessarily, and can become significant security liabilities if vulnerabilities aren't patched. Good governance and automated inventory decommissioning processes are essential to combat VM sprawl. There are also risks around VM image security, ensuring the templates used to create VMs are hardened and free of malware.
Okay, virtualization enables cloud but brings new risks. We mentioned encryption playing an enhanced role for confidentiality. Let's revisit that.
Given that your data is leaving your physical control and residing in a shared public cloud or third-party managed private cloud environment, encryption becomes absolutely vital. It's your primary technical control to mitigate risk.
Mitigate risk of what specifically?
Two main things: data in motion and data at rest. For data moving between the customer and the cloud, or between cloud services, using strong transport encryption like TLSSL is essential to prevent eavesdropping or interception. For data at rest, meaning data stored on disks or in databases within the cloud, encrypting it ensures that even if someone gains unauthorized physical or logical access to the storage media, maybe a provider employee or another tenant via vulnerability, they can't read the data without the decryption key.
And ideally, the customer manages those keys.
That's the gold standard for maximum security, especially for sensitive data. Customer-managed keys, often called Bring Your Own Key or BYOK, ensure the provider cannot decrypt the data, even under legal compulsion, without the customer's explicit cooperation. Though key management itself then becomes a significant customer responsibility.
Right. Moving on to governance, auditing and compliance seem like they'd be tricky in the cloud. How do I audit a provider's environment?
It's definitely a challenge. On the one hand, providers often offer those pre-packaged compliance solutions we talked about, which is an opportunity. But on the other hand, verifying the provider's actual controls is difficult. For obvious security and competitive reasons, CSPs are generally very reluctant to allow customers or their auditors physical access to their data centers or to share detailed internal network diagrams or configuration files.
So traditional on-site audits are usually off the table. How do customers get assurance then?
Customers typically rely on third-party audit reports that the CSP provides. The most common standards are the System and Organization Controls, SOC reports, particularly SOC2 and sometimes SOC3.
What's the difference?
A SOC2 report provides detailed information and testing results regarding the provider's controls relevant to security, availability, processing integrity, confidentiality, and donor privacy. based on the AICPA Trust Services criteria. It's usually restricted information, shared only with current customers under NBA. A CISSP 3 report covers the same criteria, but is a more high-level, general-use report that provides assurance without revealing detailed internal control information. It can often be freely downloaded from the provider's website.
So as a customer, I'd want the SOC2 if possible, but might only get the SOC3 publicly.
Often, yes. The CCSP professional needs to understand what these reports cover, their limitations, and how to use them as part of their overall risk assessment and provider due diligence. You also need to understand the concept of shared responsibility in audits. The report covers the provider's controls, but you are still responsible for auditing the controls you manage on top of their service.
Okay, makes sense. Rely on third-party attestations, but understand their scope. Now, tying all this together legally, the contract and the service level agreement, SLA, are they the same thing?
Not quite, though the SLA is usually part of or referenced by the main contract. The contract is the overall master legal agreement. It defines the broad terms and conditions, responsibilities of each party, liability limitations, except PI, remember, data ownership, governing law, confidentiality clauses, and dispute resolution processes. It's the foundational legal document.
Okay, the big picture legal stuff. What does the SLA add?
The SLA gets specific and technical. It defines the quantifiable metrics for the expected level of service. It doesn't just say the service will be available. It specifies exactly what level of availability is guaranteed, often expressed as a percentage uptime, like 99.95% availability per calendar month. It might also define metrics for performance, e.g. API response time under 500 milliseconds, support response times, or disaster recovery targets, RTRPU.
And crucially for the customer, what else must the SLA contain?
The consequences. The SLA must clearly define the remedies or penalties if the provider fails to meet those specific, measurable service levels. This usually takes the form of service credits, discounts on future bills. For example, if uptime drops below the guaranteed percentage for a given month, the customer might automatically receive a 10% or 25% credit on that month's invoice. The SLA is the mechanism for holding the provider financially accountable for performance and availability. It's where you manage the risk of poor service impacting your OPEX value. #TechCheck6. Related and emerging technologies. Exam scope.
All right, this has been incredibly comprehensive on the core architecture. The final section in this chapter looks ahead a bit, touching on related or emerging technologies that are relevant to cloud security and might appear on the CCSP exam.
Right. These are technologies that either leverage cloud infrastructure, interact heavily with it, or present new security challenges in a distributed environment. The ISC exam outline specifically lists several.
First up, machine learning, ML, and artificial intelligence, AI.
ML and AI are becoming deeply integrated into cloud platforms and security tools. These are systems designed to learn from data and make decisions or predictions without being explicitly programmed for every scenario. In security, they're used in advanced intrusion detection prevention systems, IDACSS, to spot novel attacks, in user and entity behavior analytics, UEB, to detect compromised accounts or insider threats, in automated security orchestration, SOAR, and much more. They help manage the scale and complexity of cloud security.
Makes sense. Automation and smart detection. Next, blockchain. People usually associate that with cryptocurrency.
They do, but the underlying technology has broader applications. Blockchain is essentially a distributed, immutable ledger. Transactions or records are grouped into blocks, cryptographically linked together in a chain, and replicated across many participants in a network. It's considered relevant to cloud because this distributed, shared nature often relies on cloud infrastructure for the participating nodes, and it offers a way to ensure data integrity and provide a verifiable audit trail in distributed systems, potentially useful for things like supply chain tracking or identity management in the cloud.
Interesting. Okay, what about the Internet of Things, IoT? Billions of connected devices. That sounds like a security headache.
It absolutely is. IoT refers to the vast network of physical devices, smart home appliances, industrial sensors, connected cars, medical devices, security cameras that have internet connectivity. They often collect and transmit data to cloud platforms for analysis or control. The huge security concern is that many IoT devices are built with minimal security features, have hard-coded or weak default passwords, and are rarely patched,
making them easy targets.
Exactly. Compromised IoT devices can be used as entry points into networks, or worse, aggregated into massive botnets used to launch distributed denial of service, DDoS attacks, overwhelming targets, including cloud services, with junk traffic. Securing IoT endpoints and the cloud platforms they connect to is a major ongoing challenge.
Right. Next term, Containers. We hear this a lot with Docker and Kubernetes. How do they relate to cloud security?
Containers are a form of OS-level virtualization. Unlike full VMs that package an entire OS, containers package just an application and its dependencies, sharing the host OS kernel. They are lighter weight and faster to deploy than VMs.
Okay, more efficient. Security angle.
They offer process isolation, but potentially less strong isolation than full VMs. Security focuses on securing the container images, making sure they don't contain vulnerabilities, controlling communication between containers, securing the container orchestration platform, like Kubernetes, and protecting the shared host OS kernel. Containers are also often used in bring-your-own-device (BYOD) scenarios to create secure, isolated work environments on personal devices, separating corporate apps and data from personal stuff.
Logical segmentation. Got it.
Oh.
Looking further ahead. Quantum computing. This sounds like science fiction, but potentially disruptive.
Very much so. Quantum computers leverage principles of quantum mechanics, like superposition and entanglement, to perform certain types of calculations exponentially faster than even the most powerful classical supercomputers. While still largely experimental, the major security implication is that a sufficiently powerful quantum computer could potentially break most of the public key encryption algorithms, like RSA and ECC, that currently protect internet traffic, financial transactions, and data security worldwide.
So, when quantum becomes practical, all our current encryption is potentially useless.
That's the fear. It necessitates urgent research into post-quantum cryptography, new encryption algorithms resistant to quantum attacks. It's a long-term but critical concern.
Wow. Okay, one last emerging concept, and this one sounds almost magical. Homomorphic encryption.
This is fascinating, and if it becomes truly practical and performant, it could be a game changer for cloud security. Homomorphic encryption is a theoretical type of encryption that would allow computations like searching, analyzing, or processing data to be performed directly on the encrypted data itself, the ciphertext, without ever having to decrypt it first.
Wait, you can work on the data while it stays scrambled? How is that possible?
The mathematics are incredibly complex, involving operations on encrypted values that yield an encrypted result which, when decrypted, matches the result of performing the same operation on the original plaintext. It's still mostly in the research phase and computationally very expensive right now.
But if it works,
Well,
what's the implication?
The implication is huge. Remember we said the big risk in cloud processing is that data usually needs to be decrypted, processed in the clear, at some point for the provider to work on it. Homomorphic encryption could eliminate that step entirely. You could send your encrypted database to the cloud, have the provider run complex analytical queries on the encrypted data, and get an encrypted result back, without the provider ever seeing your plaintext data or needing your decryption keys.
That would remove a massive barrier to putting highly sensitive data in the cloud. It addresses that core confidentiality risk.
Exactly. It could fundamentally alter the trust equation between customers and cloud providers if it becomes commercially viable at scale. Hashtag key learning points and recap.
Okay, phew, that was a seriously deep dive into cloud architecture, from the fundamental NIST characteristics to the emerging tech horizon. Let's try to quickly recap the absolute must-know distinctions from this foundational chapter.
Definitely. First, nail down the difference between the three service models based on who manages what. IaaS, customer manages OS, apps, data. PaaS, customer manages apps, data. Provider manages OS platform. And SaaS, customer manages users, config, data. Provider manages almost everything. Remember where that security or responsibility line shifts.
Right. And then the 4 deployment models based on ownership and access. Public shared, vendor-owned, private dedicated, single customer, community, shared by affinity group, and hybrid, mix and match.
And always, always keep the primary driver in mind. All IT decisions, especially security investments, must stem from the organization's business requirements, which are prioritized using the Business Impact Analysis, BIA. The shift from CapEx to OpEx is a key financial driver, but needs careful management via the SLA.
And that legal red line we hammered home.
Cannot say it enough. PII responsibility.
Yeah.
The customer, the data owner, is always ultimately responsible and liable for protecting PII, regardless of the provider's role or fault in a breach. Contracts cannot transfer this legal accountability.
Finally, that core vocabulary is key. Understand the economics of resource pooling and virtualization, the protective role of the CASB and its 4 pillars, visibility, compliance, data security, threat protection, and the critical difference between vendor lock-in, inconvenient, and vendor lockout, catastrophic.
If you got those core concepts down, you've built a really solid foundation for everything else in the CCSP.
Hashtag outro.
That really wraps up our foundational exploration of cloud architectural concepts for the CCSP. I think the biggest takeaway for me, and hopefully for you listening, is realizing that this certification isn't just about listing technologies. It's about deeply understanding how these different architectures fundamentally change, where responsibility lies, how risk is shared or not shared between the provider and the customer.
Well said. And maybe one final provocative thought to leave you with, building on that homomorphic encryption idea. If or perhaps when it becomes truly practical to compute on encrypted data in the cloud, how much will that change things? Think about that PII liability. If the provider literally never needs to see the plain text data, does some of that immense legal risk and responsibility we discussed potentially shift? Or will customers, conditioned by today's risks, still insist on holding all the cards, even if the technology makes it unnecessary? It could really reshape the security landscape.
Definitely something to mull over as we look at the future of securing the cloud. Great stuff. Next time, we'll build on this architectural foundation and dive into the specifics of cloud data security, looking at controls, life cycles, and governance challenges.
Looking forward to it.
Until then, thanks for joining us on AudioCert. Stay informed and stay secure.